thank you very much, Professor Kitano, for the kind invitation. And it's also my great pleasure to be here for this exciting ICC. And this very nice opportunity for me to share our research on hydride for catalytic ammonia synthesis. You know, we know that, we all know that ammonia is indispensable for our daily life, and our food, our nitrogen-containing chemicals are somehow has been derived from ammonia. And in recent years, we know that ammonia have another application, that energy carrier, because ammonia is not that stable, it's not that unstable, so that hydrogen content is pretty high. So we can treat this as an energy hydrogen carrier. Estimated by International Energy Agency, ammonia production at this moment is around 200 million tons, but till 2050, it could be double the size. And half of them would probably used for the maritime as a fuel. But we all know that ammonia production is highly carbon dioxide emission. So we need to look at we either need to improve the existing technology, or we need to look at some new methods for ammonia production, especially by using green hydrogen as a feedstock. In Haber-Bosch, we can reduce carbon dioxide emission, but we also should look at alternative processes that would use renewable energy that we either use green hydrogen or use water as hydrogen sources and to produce green ammonia. In this, under this scenario, we are looking at research activities that on thermal catalysis, on the electrochemical ammonia synthesis, and photocatalysis. And all these efforts, I'm very glad to see that in this conference that more topics, more presentations on ammonia, because we know that we are looking at something that could be somehow different from existing technology. We look at the small scale, distributed ammonia production under mild condition. So it's really challenging and important area, and there's many things we can expect it. That's new scientific understanding, and as well as knowledge would be somehow enhanced during this such a pursuit of green ammonia. So let's look at use this table to look at the knowledge we have been accumulating during the past century, that ammonia industries has been very well studied. And we know that the most Haber-Bosch process, in Haber-Bosch process, we use ion catalyst. So ion is the key components. And from surface sensor study, we know that the specific sites that's made of 7 ion atoms are very highly active dinitrogen activation. For ruthenium, also the ruthenium supported ruthenium catalyst, or there's also the nano-sized ruthenium particle, and this unsized particle, we're looking at sites that made of 5 ruthenium atoms that make a highly active site for dinitrogen activation. Very interesting that it's still a kind of controversial understanding on another important component we call it electronic promoter. We know that alkaline earth oxide, hydroxide, highly would strongly enhance the catalytic activity of iron and ruthenium. But what's the role they play in the catalysis is still under debate. And so, that I would like to bring your attention to this point, because today I'm going to talk about alkaline earth hydride for ammonia synthesis. It's not in an oxide form, it's in a hydride form. However, they have some correlations I would like to discuss later. And of course, in both iron and ruthenium catalyst, we have a common understanding that dinitrogen dissociation, splitting directly on the surface, would be a kinetically slow step. And so this explains that why we need to apply high temperature, high pressure for Haber-Bosch process, because most people, we believe that is very kinetically difficult because the triple bond of dinitrogen is too stable to be broken at low temperature. But this is the case for all the trace metals or metals. So I would like to show this very this milestone work from Professor Ertl in his beautiful surface science study on clean iron surface. If you look at this elementary step, you will see that dinitrogen splitting on clean iron surface is not that difficult. At least some surface evidence shows that dinitrogen dissociation on surface ion become absorbed nitrogen species could occur even below room temperature. However, if you look at the lowest, the stablest state here, it's just absorbed nitrogen, it's very stable. And if you want to hydrogenate that nitrogen to ammonia, you need to overcome a barrier or need uphill up to 250 kilojoule per mole. So that means that at room temperature, you won't be able to hydrogenate this this surface nitrogen to ammonia. So you have to reach temperature. And similarly, on ruthenium surface or on other transmetal surface, people realize that this is a very nice work from Professor Noskov, shows from theoretical point of view. He shows that if you have catalysts that can dissociate dinitrogen easily, you may not be able to hydrogenate to ammonia easily. So there's a kind of scaling relations between or among the intermediate species on the surface of ruthenium or other trace metals. So for effective catalyst, you probably have to find some trace metal that won't bond nitrogen atom so strongly, no bond NH or no so weakly. You need to make a compromise. So that's explain why we have this volcano shape that shows that iron, ruthenium, and copper molybdenum alloys they are commonly investigated or used for ammonia study, ammonia production. And I also want to show that instead of a transition metal, dinitrogen activation over some of the alkaline earth metal is not difficult. For example, for lithium. Lithium, if you have clean lithium without oxide covered on the surface, exposed to that dry nitrogen atmosphere, it will gradually become brown, red colored. It is become nitride. It's pretty easy at room temperature. However, it's a bit difficult to remove nitrogen from lithium nitride because it's kind of interaction between hydrogen molecules is not that easy. But I will show something that our findings give some different interpretation. So that we will see that very recently, researchers progress from Professor McFarland and Professor Noskov and Chokentov, they use lithium as to mediate nitrogen fixation ammonia formation by using electrochemical way. They fix nitrogen by lithium and hydrolyze lithium nitrate into ammonia and produce lithium cation compounds. And it has to apply high voltage to regenerate lithium back to lithium cation to lithium and react with dinitrogen become lithium nitrate. This makes this whole process a cycle. So that's the way making ammonia from alkaline metal. Nitrogen fixation not a problem, but you need to apply energy to bring ammonia from that. And so we all know that for Haber-Bosch process, we use hydrogen molecule as hydrogen sources. In biochemical system, in enzyme or in molecular system, people are using protonic hydrogen as hydrogen source. But how about hydrated hydrogen? Hydrated hydrogen is somehow compared with other two hydrogen species. They are electron rich, and they are highly reductive. In dinitrogen reduction to ammonia, this process needs electron and also needs hydrogen. So how about hydride? And I will show that this is not a new topic, and half century ago that people in molecular system, they have been looking at hydride, or both late transition metal or early transition metal. For late transition metal like cobalt, when they form hydride complexes, they introduce dinitrogen, you will see that hydrogen will undergo reductive elimination as molecular hydrogen and leave electron to the transition metal center. And by doing so, dinitrogen can be effectively activated. But in this case, for late transition metal hydride, no NH bond formation, because hydrogen all really eliminated as molecular hydrogen. And in recent years, research from Professor Ho's group has made a titanium and chromium transition metal hydride. This is an early transition metal hydride. Something different, that when you introduce dinitrogen to this hydride, you will see that those hydrides, part of hydrogen undergo reductive elimination, part of hydrogen undergo reductive protonation. That means that you will be able to have NH bond formed during such interaction. However, the thing is that in either case, we won't be able to produce ammonia catalytically because either there's no NH bond formation or the NH bond and the transition metal nitrogen bond is too stable to be hydrogenated. So let's come to our research on alkaline earth hydride for ammonia. This research is actually somehow derived from our previous research on hydrogen storage. We use lithium nitride as the hydrogen storage material, and if you look at this reaction, it's stepwise hydrogenation. And we want this hydrogenation stop at lithium amide plus hydride. And this fully reversible reaction, this is very good for hydrogen storage. However, in our experimental finding, we always observe ammonia formation during hydrogenation and dehydrogenation. And later we realized that the amide will be able to hydrogenate into ammonia and regenerate hydride. So this is some understanding from hydrogen storage research. So we have hydride there, we have ammonia, but can we go back to lithium nitride? The answer is not that easy. However, we can use lithium hydride to react with nitrogen to see what happens. And this reaction is pretty new, that we realize that lithium hydride can react with dinitrogen, become lithium amide plus hydrogen if you apply certain temperature. This reaction shows that the dinitrogen is reduced into NH, and hydrogen undergo both hydrogen reductive elimination and protonation. We have NH bond formed, we have hydrogen molecule generated. And this means it's quite similar to early transition metal hydride. But if you look at the second reaction, it's a hydrogenation process produce ammonia. This is very different because that, in this case, hydrogen undergoes heterolytic splitting, produce both hydrated hydrogen in the form of lithium hydride and protonic hydrogen in the form of ammonia. So these two reactions together, you will be able to show that lithium hydride mediates the ammonia synthesis process by using dinitrogen and dihydrogen as feedstock. So that's chemical reactions explains that, or indicate that ammonia formation can be mediated by alkaline earth hydride. So we have experimental results to show that this reaction, not only lithium but barium and calcium hydride, they can do nitrogen fixation, and it can also, after forming amide, it can do hydrogenation with ammonia. So that's make a strong basis for our understanding that hydride would be essential. It could play an important role in ammonia synthesis. So let's come to our first case of study on catalytic development, catalyst development for ammonia synthesis. We bring transition metal with lithium with hydride together to see what happens, and whether lithium, the alkali hydride, function as a conventional electromolecular promoter as we use in carbon-Bosch process, or they are something different. And it can show, I won't give too much details, but I will show this two figures. You can see that we mixed lithium hydride with 3D metals starting from vanadium to nickel. You can see that some of the transition metals, like chromium, manganese, iron, cobalt, nickel, cobalt, they show catalytic activity starting from 150 degrees Celsius. And at a higher temperature, both vanadium and nickel also show catalytic ammonia formation. This is very different from our conventional understanding. If you look at the figure on the right, the black curve shows that in 3D metal, only iron are catalytic active. Yeah, we all know what's the reason for that. However, if you hydride there, you will be able to have the activity increasement by at least 4 orders of magnitude for for chromium and manganese. So that's really, really exciting for us when we look at this figure. This figure shows that when lithium hydride comes into the picture, the catalytic activity for all 3D metal, no matter it's early or late, they are all catalytic active. And think about it further, it shows that with lithium hydride, the catalytic activity seems to have less transition metal dependence. This is very different from our conventional understanding on the volcano curve active shape, that only group 8 element shows better catalytic activity. But this is very different with hydride. And we further optimize our catalyst, and we'll be able to further improve the activity of this hydride and transition metal complex. This is composite catalyst. If you disperse on this on magnesium oxide, you will be able to increase the activity by 3 times. And if you won't allow contaminate water, oxygen into your reacting system, you will be able to run the catalyst for thousands of hours. So that shows very promising catalytic performance. So with this funding, we're starting to think about that. We still have some catalyst that made of transition metal, made of either 7 iron atoms or 5 ruthenium atoms for the active sites. For the dynamic activation, this alkaline earth hydrides function as conventional electronic promoter. So this is our stimulate us, motivate us for the further understanding. And I thank our collaborator, Professor Jiang. Someday, a few years before, he approached me that whether we can collaborate to look at our catalyst and in his system. He has a vacuum system. He can use laser to bombard on the system on the catalyst and see the gaseous cluster formed from the catalyst. So we send our catalyst, lithium ion, is composite mixture to his laboratory, and he used his laser to bombard on our sample, and we are very, very surprised to see that we observe a kind of ternary hydride formed. The ternary hydride is made of lithium ion and hydrogen. Hydrogen somehow is bound with ion, and lithium is this cation is neutralized this cluster. And more interestingly, if you introduce nitrogen into the gaseous phase, you immediately observe the NH2 species formed. So that means that this cluster, this complex hydride cluster, can immediately can be highly reactive to that nitrogen to protonate, to dissociate, and to protonate to NH bond. So that's this experimental results inspired us to look at whether we can form a complex hydride, like a hydrogen bond with transition metal, then they form anion. Then the alkaline earth is cation make a neutral hydride that we call complex hydride. And people in hydrogen storage know that there's huge knowledge in transition metal hydride and also complex hydride. So we know that we can use alkaline earth as cation and look at this cation with an anion made of transition metal hydrogen. And I'll pick up ruthenium as a starting case because ruthenium hydride can be easily made. And my student CHEN Ru, I just mixed the ruthenium lithium hydride together, and hydrogen is mixture at 400 degrees Celsius. It can readily get lithium ruthenium hydrogen. This species. This is a spark-based material. It is very different from conventional ruthenium metal. You will easily see that because ruthenium now is positively charged. It bonds with hydrogen. It has a long distance between ruthenium cluster. Ruthenium hydrogen and ruthenium hydrogen is long distance. And the hydrogen bond with ruthenium is somehow negative charged, and so do lithium. So we have these ionic compounds. It have some ionic nature. This compound is complex. And let's see what happens for those compounds for ammonia catalysis. You can see here is that when we introduce ammonia, when we introduce hydrogen and nitrogen into the system, we observe much enhanced catalytic activity. If you compare with ruthenium catalysis without lithium and barium, the activity could somehow at low temperature can be reduced, starting temperature can be reduced by 100 degrees Celsius, and you can see compared to the red line, blue line, compared with the green line, you can see the huge change for that. We also looked at what's the lowest temperature the complex hydride could do for ammonia, and we collaborate with our colleagues in DSA, Professor Lee, and we look at even at 50 degrees Celsius, we can still observe very small amount of ammonia formed catalytically. Although it's very small, very low rate, but still it's catalytic formation. So that's very interesting system. We want to know what's happened, how that nitrogen can be activated, how hydrogen can take place over this system. So we collaborate with Professor Thijs Week from DTU, and we spent almost 2 years to look at this very complicated system because the surface is have hydrogen, lithium, ruthenium there. The hydrogen content, the ruthenium, the coordination number of ruthenium all play important role on the nitrogen activation and hydrogenation. And finally, we identify this 13-step reaction path. And the key message here is that over such a surface, the nitrogen splitting into atomic nitrogen is not that favorable because it's the nitrogen couldn't find a suitable place, comfortable place to stay. On the contrary, on the other hand, the dinitrogen can somehow absorb on the surface and undergo hydrogen-associated activation process. That means that before dinitrogen dissociation, hydrogen will bond with dinitrogen, become N2H, N2H2, then splitting into NH. This is one of the message. The other message is that during the hydrogenation, the lattice hydrogen, the lattice hydride, would be the reacting hydrogen species. It would undergo reductive protonation and bond with nitrogen. Then the hydrogen vacancy left in the lattice will be somehow filled by the molecular hydrogen. This is another message. And also some other messages that I would like to highlight maybe here is if you look at step 10, that before ammonia released from the catalyst surface, ammonia only bond with lithium. So that's also very interesting because we know that in conventional understanding that ammonia, the nitrogen always bond with transition metal. But here, something very different. So I'd like to give some details on the first step, hydrogenation. If you look at the very first one, here is the nitrogen coming to the surface. You will see that one nitrogen bonds with ruthenium, and the other nitrogen, that is electron-rich part, it is stabilized by lithium. Lithium, ruthenium work together to stabilize that nitrogen. And then after that, the lattice hydrogen undergo reductive protonation and eventually bond with nitrogen to form N2H. In this process, you only need 0.6 electron volts. It's not that big issue. That it seems that this would be easily happen under milder condition. So that explains that that in this electron-rich and multiple components surface, you will be able to do something very different from a transition metal surface that both lithium, hydroxide hydrogen, and ruthenium will work together to activate that nitrogen and do the hydrogenation. So that's something that I would very much share with you. This is really, we are very excited when we look at this picture. And also remember that I mentioned that during the final state of ammonia formation, the nitrogen only bond with lithium. So that's 2 years efforts with collaboration from experimentalist and theoreticists is the way we can stimulate a lot of understanding on ideas on this system. So this is one of the consequences, one of the things that we inspired from the theoretical investigation that can we use alkali hydride alone without transition metal? Can we do this? Can we do ammonia synthesis alone? And but when we look at this, we are not directly go to this. My colleague, my student CHEN, he gave a presentation yesterday. He looked at the barium hydride first, and he used high temperature to remove some hydrogen from barium hydride and create hydrogen vacancy. And he realized that nitrogen can be fixed on that hydrogen vacancy surface. Then we think whether we can create a hydrogen vacancy by some other way, not by thermal energy, but by some other things, like photo energy, because some hydride are semiconductors. For example, lithium hydride have band gap from our experimental results is 3.7 electron volts. So if you apply UV, you'll be able to excite the surface. And this phenomenon is very different from conventional semiconductor made of oxide, because in that case, if you introduce UV, the electron-hole separation, and they will immediately neutralized. But for hydride, it's very different. The thing is that when we shine light on the hydride, we observe hydrogen desorption from the surface. And the hydride become gray-colored. You can see that. The hydrogen released from the surface, and the surface become dark-colored. And we look at EPR, we observe strong signal that shows that electrons is there. So it's long-life electron, photogenetic electron. Where is this possible? Because hydrogen removed from the surface, the hydride is oxidized, probably oxidized by the hole, and eliminate as molecular hydrogen. It's reductive elimination. Hydrogen is gone. And electrons there, electrons left on the surface. So we can use that electron to activate that nitrogen. And before I go to the dinitrogen fixation, I will show that our calculation shows that remove hydrogen from lithium hydride surface, no matter it's 100 or 111, the UV is sufficient to remove two hydrogen atom from surface to generate a vacancy. Then we introduce dinitrogen to the system, and the UV, we successfully observe NH stretch by IR, and if we increase temperature and use hydrogen, we'll be able to detect ammonia formation. And at that time, we observed the nitrogen fixation rate of 500 mmol per gram catalyst per hour. So that's have been confirmed the results because it's NMR and IR and other techniques to detect ammonia. So this shows that, without transition metal, if you use UV, you'll be able to activate your hydride, you'll be able to fix the nitrogen on the neat lithium hydride surface. Then can we do this catalytically? And I raised a question to CHEN, and CHEN tried a couple times, but he replied to me, we cannot make ammonia catalytically. But however, we discuss on that, because UV will generate hydrogen from your surface, then the surface could be highly hydrogen partial pressure sensitive. So can we use mixed gas with high concentration of nitrogen, but slightly low hydrogen partial pressure? Then some very interesting results comes out when we introduce a mixture of dinitrogen and dihydrogen with 10:1 molar ratio. Under this condition, we'll be able to detect ammonia formation for catalytically. It's catalytic formation of ammonia, although the rate is not that high. But this is under UV, the temperature is not that high. And now we can, we haven't finalized the result, but now we can increase the activity by 20 times. So that shows that if you can optimize the condition, you'll be able to produce ammonia catalytically. So let me discuss a little bit more on the catalytic dinitrogen activation modes over hydride and compare with transition metal surface. We know that over transition metal surface, dinitrogen directly splitting into atomic nitrogen and bond on the surface of transition metal. For example, the ion from clean surface ion. And the nitrogen stay there will undergo stepwise hydrogenation to ammonia. So this is our common understanding on dinitrogen activation and ammonia formation over transition metals. However, when we have lithium hydride here, it is it's compounds. So dinitrogen is not that easy to be split directly into nitrogen atom to absorb on the surface. We did preliminary calculation that shows that that's not very stable. It's uphill. We couldn't do this on the surface from theoretical calculation. However, when you just introduce nitrogen to lithium hydride, like this two chemical reactions with each other, you probably need a high temperature. For example, lithium hydride and dinitrogen reaction, our experimental results shows that you need to reach temperature about 400 degrees Celsius. Then you'll be able to form a lithium imide. So that means that dinitrogen activation on lithium hydride is not that kinetically feasible, kinetically feasible. So what can happen for that? As showed in our last results is that when we use ultraviolet radiation, we'll be able to remove hydrogen from a surface, create an electron-rich surface, and then dinitrogen can be active and can be easily activated over that surface. So that's a very first message I'd like to share, that you need some vacancy bond, vacancy on the surface to activate that nitrogen. And if you look at the hydrogenated step, you will see something also very different from transition metal is that the hydric hydrogen in the lattice would undergo reductive protonation. This is in hydratic space. The lattice hydride would somehow undergo protonic reductive protonation and bond with nitrogen. This is very different from transition metal surface. That is, in transition metal surface, we use splitting hydrogen atoms and bond with nitrogen atom. And in lithium case, no matter what's the chemical state of the nitrogen, it always bonds with lithium. It always bonds with lithium. So nitrogen bonds with lithium, but in transition metal, it's always bond with transition metal. And then before dissociation, dinitrogen, we will be able to have N2H species, although we didn't observe such species experimentally, but can be also understand because it's not as stable. It can dissociate into NH species. That species we observed. It can be observed easily by IR. So that in that case, the splitting of dinitrogen is not directly on the surface, but undergoes certain hydrogenation and then split into NH species. And finally, the hydrogen, molecular hydrogen would undergo heterolytic splitting to minus hydrogen and protonic hydrogen, and regenerate the hydride surface and give out ammonia. So that's a very different profile that, let's say that perhaps the electrons was very important and the catalytic active sites, composition of active sites also important. And I remember yesterday, Dr. Rochi, he also showed something on very interesting work on barium hydride activation on the nitrogen, and he shows that that's vacancy is very important, and we also need to create a vacancy on barium hydride for dinitrogen activation. And then one further discussion, and when you have hydride here, how about transition metal help on hydride? What's the role transition metal performed for that dinitrogen activation? And then our understanding, we are still learning, but at this moment, our understanding is that transition metal would somehow form kind of a complex species with alkaline aqueous hydride. And this transition metal would help on the protonic reductive protonation and reductive elimination, make those steps easier. So that's why when we have lithium hydride mixed with transition metal, we'll be able to have thermocatalytic performance at low temperature, come with neat hydride. So that's the things we have been learn from our experimental theoretical investigation. I believe similar observation also from Dr. Rochi when we look at the barium hydride, the dinitrogen activation conversion over barium hydride, similar understanding on the activation of facilitating the reductive protonation. So then I would like also bring this slide to show that lithium hydride, sodium hydride, barium hydride, they all have potential to be catalytic active if you have applied suitable condition. For example, lithium, you use UV to give energy to that to the system. For barium, you probably you have your energy, but for potassium, sodium, you under give plasma condition, you'll be able to produce ammonia. I'm not have time to discuss this this time. And also later, Dr. Peter Yan will talk about this potassium with carbon, and it also can be thermally catalytically effective. So that's very interesting area that I believe with a lot of information understanding will be generated in the future. So finally, I'll just show that I hope I could convey the message clearly that when hydride come into this picture, that the dinitrogen activation, ammonia formation would undergo different mechanism. And with hydride, we'll be able to observe that we have less dependence on transition metal, and we'll be able to form ammonia under mild condition. And this is because there's nitrogen, very beautiful chemistry among alkaline aqueous metal with hydrogen, nitrogen, ammonia. Please look at this, our papers, but I hope I could have time to explain more, but I will show that this is that number of very interesting chemical reactions there that allows alkaline hydride catalytic effective. Then finally, I'd like to acknowledge those very brilliant young researchers that make a great contribution to our research, and they are derived from their excellent work. And also a very nice collaboration with our collaborators and great support from the agency. With this, I'd like to thank all for your kind attention. Thank you.